Hey guys, welcome once again to this problem solving session. This problem we consider, it says that we have a chain effectively which is going to fall through a hole in the middle of a table, and we have to find out the time after which the two ends of the chain strike the floor. The length of the chain is 1 meter, and that the height of the table is also 1 meter. First of all, let us set up the situation. Let us imagine, or let's use variables. That is a very good way of solving problems. I'm going to call, in this case, the length of the chain as well as the height of the table as L, so that L is 1 meter and the height of the table is also 1 meter. It's given that the chain is having no friction at all. Let us say the total mass of the chain, which is not specified. It's an example of a variable that is unknown but that is unwanted as well. So let's say total mass, or we can better consider the linear mass density of the chain. We suppose that the mass per unit length of the chain, which is assumed to be uniform. So mass per unit length, let's call it as lambda. So lambda is nothing but mass of the chain divided by the total length. Now, if you carefully consider the situation, we first of all notice that if you, instinctively try to apply the energy conservation, that will not be giving us a correct result. The reason is the inelastic impacts going on at the end, where the moving part of the chain that pulls on some part which is on the table already. These are inelastic impacts, and that is why the energy is lost actually. So we cannot actually conserve the energy in this case. If the chain was laid down straight on the table and then was falling so that every link has the same speed always, then the energy might be conserved. In fact, that then if we do not have any friction on the table surface, then the energy will be conserved actually. However, in this case, the energy method will not be useful. It will be actually giving us a erroneous result if we apply it actually. So we will have to look at the momentum part actually. Now, let us say that at some moment, uh, the chain has come down uh, a length y. Let's draw the chain in a bit. Say the rest of the part is heaped on the table over here, and this length of the chain, I've drawn a straight line just for the reference. Difficult to draw the chain as such. This is y at this moment, and the velocity of the chain at this moment, because y is the length from here, the top to the bottom of the chain. So the velocity is nothing but dy by dt. But let's say the speed, we just call it as v, which will be the same for the entire chain, whichever is moving actually. Now, if you consider the forces acting on this chain, obviously we have a force of gravity pulling the entire chain down, and that force will be, in this case, the mass, which is lambda into y into g, that's mg. But also there is actually a force exerted at the top by the part which is at rest on the part which is moving. It actually comes because of exchange in the momentum actually. If you see carefully in this case, just a very little time dt later, a length v dt will have been added to the chain. Assume that this time is not long enough so that the velocity has not changed significantly. We can still take it to practically v. So the part which has been added up that is lengthwise v into dt. v dt is the length which has been added up. So the mass which has been added up is lambda into v dt. That is the mass which is added up actually. So in the next, let us say this part over there, during the mass added is lambda into v dt, which implies this much of extra momentum has been added up. Or conversely, if you consider this part which was at rest, this part is abruptly brought into motion with a speed v, which implies momentum has abruptly been increased. So this impulse is actually coming from the falling part of the chain. It exerts on that part which has been added up an impulse which is lambda vdt into v, and therefore we can see that this is the average force exerted, and therefore the momentum added up is lambda v square dt. This must be coming from the reaction, or this must be, you might consider this to be basically creating an average force, the force which the falling part is experiencing due to that extra, the upper part actually, which is in fact very tiny, but basically brings with itself a certain amount of force pulling in the upward direction. So the average force which is being exerted on the falling part by the portion which is just at the top over there, okay, that has to be speeded up, is simply the momentum added up by the time, which is lambda into v square. So this is the extra force coming up on the chain acting the upward direction due to the upper part of the chain, which is actually just going to get added up in fact. As a result of which, if you look at dynamics, I can write down the equation governing the motion of the particular part which is in motion actually. That we'll have to scrub it. So we could write down for the chain the relevant equation governing the dynamics of the chain, that is mass into the acceleration, that is lambda y into the acceleration a. This will be the net downward force, which is the force of gravity, minus lambda into v square. Now dividing in this case by lambda into y gives us an equation which is this. This is actually speaking strictly, this is a differential equation because a is du by dt, but I will be involving a lot of variables. V is unknown, y is unknown, and t is also there actually. This can be solved by the usual means of solving a differential equation that we have, by basically multiplying an integrating factor to make it an exact differential. However, we can also do it in a very clever way actually. First of all, you should notice that the acceleration is less than g because we are subtracting something positive. Now, if it happened, for example, had the acceleration been a constant, then v square by y would have been twice a actually, because for constant acceleration with an initial zero speed, v square must be twice a into displacement, which is y at the lower end actually. So this is what we should have. Then in this case, then what should happen? And plugging it back in the previous equation, we would have got a equal to g minus 2a, giving us 3a equal to g, which gives us a equal to g by 3, which is indeed constant. So that implies that our assumption is valid. The assumption of assuming this constant acceleration indeed coming up to be so in this case, which implies it should be the acceleration actually. Had we assumed that the acceleration is a constant but ended up getting the acceleration not to be a constant, then our assumption would have been wrong, and then we'll have to go back and solve the equation the informal way. But at least in this case, we are luckily saved, and we find in this case therefore that the acceleration is actually g by 3. And therefore the leading end, the first end, as the chain falls, it is actually moving with a constant acceleration of g by 3. So the time at which the first end, leading end, the time t1 at which the leading end strikes the floor is obtained by the equation half at1 square equal to L, giving us t1 equal to twice L by A, which is turning out to be 6L by G. This gives us time t1 by plugging the values, that turns out to be approximately 0.78 seconds. This is after, therefore, after the beginning, this is the time at which the first end strikes. Now, once this time, as the chain falls and this time has elapsed, by this time, the chain has become basically straight, vertical. The entire length of the chain is in air because length of the chain is also L, which is the height of the table. So from this moment onwards, the top end is going to just be in free fall subsequently, and therefore, well, the speed of the chain at this moment will be how much? At this moment, this chain will have a speed, the entire chain actually, that is equal to v1, which is at1, that is g by 3t1, that turns out to be root of twice gl by 3, that is approximately giving us, upon plugging the numbers, a value that is around 2.56 meter per second. And from this moment, the chain comes out in free fall. The upper end therefore is going to travel a distance L with an initial speed which is 2.56 meter per second, which is v1, and the final total displacement being equal to L. So the time taken by the lower end, so the latter end, the upper end, to fall, that is given by the equation v1t plus half gt square equal to L. Upon solving this equation, the quadratic that we have, it gives us the value of t as root of twice L by 3g. Root of twice L upon 3g, which is turning out to be in effect 1/3 of the previous time, and that is around 2.26 seconds actually. Therefore, from the beginning, the upper end is going to strike or the back end over there. Total time T2, that is from the beginning, which is turning out to be 0.78 plus 0.26, which is around 1.04 seconds from the beginning. After the start of the process, basically. Okay, so that is what we have in this case. The important thing that we have to remember in this particular situation is the idea that the energy conservation can't be applied over there. The reason why it can't be applied is because the energy is not conserved, because in inelastic impacts going on, the energy is getting lost actually. That is why we must revert back to the momentum. That is always going to give us the correct result. Okay. I hope this is going to be useful trick, which is useful for exams like the KPUI or even the other exams, IDJs for example. Okay, that will be all for today then. The next question will take up in the next video. Thanks for watching.